the total length of primary and secondary conductors connected to a transformer exceeds 25 feet, the feeder tap rules in 240.21 b3 are not applicable. In this scenario, 210.20 should be used for sizing both the primary conductor and the overcurrent protective device, or OCPD, in the subpanel. Firstly, calculate the total load connected to the secondary side of the transformer. This involves summing up all the individual loads that will be supplied by the transformer. Secondly, use 210.20 to determine the minimum ampacity required for the primary conductor. The primary conductor's ampacity must be sufficient to handle the total load current drawn by the transformer. Thirdly, again using 210.20, determine the appropriate ampacity for the OCPD located in the subpanel. The OCPD's ampacity must be adequate to protect the primary conductor from overcurrent conditions. The requirements of 210.20 may necessitate the use of a larger conductor size or a higher OCPD ampacity compared to what would be permitted under 240.21 b3. This difference arises because 210.20 explicitly considers the voltage drop that occurs along the length of the conductors. To illustrate this point, let's consider an example. Suppose a subpanel is situated 50 feet away from a 480 volts to 208/120 volts transformer. The total load connected to the transformer is 100 kilovolt amps, and the primary voltage is 480 volts. If we were to apply 240.21 b3, the minimum conductor size for the primary conductors would be 1/0 American wire gauge copper, and the minimum ampacity of the OCPD in the subpanel would be 125 amps. However, when we apply 210.20, the results differ. The ampacity of the primary conductor must be at least 140 amps, and the ampacity of the OCPD in the subpanel must be at least 150 amps. As this example demonstrates, 210.20 often mandates a larger conductor size and a higher OCPD ampacity than what 240.21 b3 would require. This is because 210.20 specifically accounts for the voltage drop that occurs over the length of the conductors, ensuring that the voltage at the load remains within acceptable limits. Therefore, always consider the total conductor length and apply the appropriate code sections to ensure safe and reliable operation of the electrical system. Remember to always consult the latest edition of the National Electrical Code, or NEC, and local amendments for specific requirements in your jurisdiction. Now, let's delve a little deeper into the concept of voltage drop and why it's important to consider when sizing conductors. Voltage drop refers to the reduction in voltage that occurs as electricity flows through a conductor. This drop is caused by the resistance of the conductor to the flow of current. The longer the conductor and the higher the current, the greater the voltage drop will be. Excessive voltage drop can lead to several problems. Firstly, it can cause equipment to operate inefficiently or not at all. For example, motors may run slower, lights may dim, and heaters may not produce enough heat. Secondly, voltage drop can damage equipment. Undervoltage can stress electrical components and shorten their lifespan. Thirdly, voltage drop can create safety hazards. Overheated conductors due to excessive current draw can increase the risk of fire. The NEC specifies maximum allowable voltage drop for different types of circuits. For feeders, the recommended voltage drop is no more than 3%, and for branch circuits, it's no more than 5%. These limits are in informative Annex D in the NEC. To calculate voltage drop, you can use the following formula: voltage drop equals current times resistance. The resistance of a conductor depends on its material, length, and cross-sectional area. Copper and aluminum are the most common conductor materials, with copper having lower resistance. The longer the conductor, the higher the resistance, and the larger the cross-sectional area, the lower the resistance. The NEC provides tables that list the resistance of different types and sizes of conductors. When sizing conductors, it's essential to consider the voltage drop to ensure that it stays within acceptable limits. If the calculated voltage drop exceeds the recommended limits, you'll need to increase the conductor size to reduce the resistance. In addition to voltage drop, Other factors to consider when sizing conductors include ampacity, temperature rating, and directing factors. Ampacity is the maximum current that a conductor can safely carry without overheating. The NEC provides tables that list the ampacity of different types and sizes of conductors based on their insulation type and ambient temperature. The temperature rating of a conductor refers to the maximum temperature that the conductor's insulation can withstand without degrading. It's important to choose conductors with a temperature rating that is suitable for the environment in which they will be installed. Directing factors are adjustments to the ampacity of a conductor that are required under certain conditions. For example, if multiple conductors are bundled together, their ampacity must be derated to account for the increased heat buildup. Similarly, if conductors are installed in a high ambient temperature environment, their ampacity must be derated to account for the reduced heat dissipation. When sizing conductors for a transformer feeder tap, it's crucial to consider all these factors to ensure that the conductors are adequately sized to carry the load current, minimize voltage drop, and operate safely within their temperature rating. The National Electrical Code, or NEC, provides detailed guidelines and tables for conductor sizing, ampacity, voltage drop, and directing factors. It is highly recommended to consult the NEC and other relevant standards and regulations when designing and installing electrical systems. Now let's talk about overcurrent protection. Overcurrent protection is a critical safety feature in electrical systems. It's designed to protect conductors and equipment from damage caused by excessive current flow. Overcurrent can result from various factors, including short circuits, ground faults, and overloads. Short circuits occur when there is an unintended low resistance path between two conductors, typically between a hot wire and a neutral or ground wire. This results in a very high current flow, which can quickly damage conductors and equipment. Ground faults occur when there is an unintended path between a hot wire and ground. This can happen if the insulation on a wire is damaged or if equipment is not properly grounded. Ground faults can also result in high current flow and pose a shock hazard. Overloads occur when the current flow in a circuit exceeds the ampacity of the conductors or equipment. This can happen if too many appliances or devices are connected to a circuit. Overloads can cause conductors to overheat and potentially start a fire. Overcurrent protection devices, or OCPs, are designed to interrupt the flow of current in the event of an overcurrent condition. The two most common types of OCPs are circuit breakers and fuses. Circuit breakers are electromechanical devices that automatically trip and open a circuit when an overcurrent is detected. They can be reset and reused after the fault has been cleared. Fuses are overcurrent protection devices that contain a fusible link that melts and opens the circuit when an overcurrent occurs. Fuses must be replaced after they have blown. The NEC specifies the requirements for overcurrent protection in electrical systems. It mandates that all conductors be protected by OCPs sized to protect the conductor's ampacity. The OCP should be selected based on the conductor's ampacity and the type of load it serves. For example, motor circuits require special OCPs that can handle the high inrush current that occurs when a motor starts. When selecting an OCP for a transformer feeder tap, it's essential to consider the transformer's primary and secondary currents, as well as the conductor's ampacity. The OCP should be sized to protect the primary conductors from overcurrent, while also allowing the transformer to operate at its rated capacity. In the example we discussed earlier, where the primary conductor ampacity was determined to be at least 140 amps based on 210.20, the OCP in the subpole should be rated at 150 amps. This rating provides adequate protection for the primary conductor while also allowing for some margin of safety. It's important to note that the OCP rating should never exceed the conductor's ampacity. Doing so could result in the conductor overheating and potentially causing a fire. In addition to selecting the appropriate OCP rating, it's also important to ensure that the OCP is properly installed and maintained. Circuit breakers should be tested periodically to ensure that they are functioning correctly. Fuses should be inspected regularly for signs of damage or deterioration. Proper overcurrent protection is essential for ensuring the safety and reliability of electrical systems. It protects conductors and equipment from damage caused by overcurrent and helps prevent electrical fires. Now let's delve deeper into the specific requirements for transformer overcurrent protection as outlined in the National Electrical Code, or NEC. The NEC provides detailed guidance on how to properly protect transformers from overcurrent, taking into account various factors such as the transformer's size, voltage, and application. Section 450 of the NEC covers the requirements for transformers, including overcurrent protection. This section specifies the maximum allowable octave ratings for both the primary and secondary sides of the transformer. The primary octave is intended to protect the transformer itself from overcurrent, while the secondary octave is intended to protect the secondary conductors and equipment. The NEC allows for different methods of overcurrent protection for transformers depending on their size and voltage. For small transformers, such as those rated less than 600 volts and with a primary current of less than 9 amps, the primary octave can be sized up to 167% of the transformer's primary current. For larger transformers, the primary octave is typically limited to 125% of the transformer's primary current. The secondary octave, on the other hand, is typically sized based on the ampacity of the secondary conductors. The NEC also allows for the use of coordinated overcurrent protection, where the primary and secondary octaves are coordinated to provide optimal protection for the transformer and the connected equipment. Coordinated overcurrent protection involves selecting octaves with different time current characteristics so that the secondary octave will trip before the primary octave in the event of a fault on the secondary side. This helps to minimize the impact of the fault and prevent damage to the transformer. When selecting octaves for a transformer, it's important to consider the transformer's inrush current. Inrush current is the high current that flows into the transformer when it is first energized. This current can be several times the transformer's rated current and can potentially trip the octave. To prevent nuisance tripping, it's often necessary to use octaves with time delay characteristics that can withstand the inrush current. In addition to the NEC requirements, local codes and regulations may also impose additional requirements for transformer overcurrent protection. It's essential to consult with local authorities to ensure that all applicable codes and regulations are followed. Proper transformer overcurrent protection is crucial for ensuring the safe and reliable operation of electrical systems. It protects the transformer from damage caused by overcurrent and helps prevent electrical fires. By following the NEC guidelines and consulting with qualified professionals, you can ensure that your transformer is adequately protected. Let's move on to discussing the practical considerations for installing transformer feeder taps. When installing a transformer feeder tap, there are several important factors to consider to ensure a safe and reliable installation. Firstly, the location of the tap is crucial. The tap should be located as close as possible to the transformer to minimize the length of the tap conductors. This helps to reduce voltage drop and improve the overall performance of the system. Secondly, the tap conductors must be properly sized and protected. As we discussed earlier, the tap conductors must be sized according to 210.20, considering the total load connected to the transformer and the voltage drop. The tap conductors must also be protected by an octave size to protect the conductor's ampacity. Thirdly, the tap conductors must be properly terminated. The terminations must be made using approved connectors and methods to ensure a secure and reliable connection. Fourthly, the tap conductors must be properly supported. The conductors should be supported at regular intervals to prevent them from sagging or coming into contact with other objects. Fifthly, the transformer must be properly grounded. Grounding is essential for safety and helps to prevent electrical shock hazards. The transformer should be grounded according to the requirements of the NEC. Sixthly, the installation must comply with all applicable codes and regulations. Local codes and regulations may impose additional requirements for transformer feeder taps. It's essential to consult with local authorities to ensure that all applicable codes and regulations are followed. In addition to these practical considerations, it's also important to consider the environmental conditions in which the transformer and tap conductors will be installed. If the equipment will be exposed to harsh environmental conditions such as extreme temperatures, moisture, or corrosive substances, it's necessary to select equipment and materials that are specifically designed for those conditions. For example, if the equipment will be installed in a damp or wet location, it's necessary to use waterproof or rain-tight enclosures and fittings. Similarly, if the equipment will be exposed to corrosive substances, it's necessary to use corrosion-resistant materials. Proper installation of transformer feeder taps is essential for ensuring the safe and reliable operation of electrical systems. By considering all these factors and following the NEC guidelines, you can ensure that your transformer feeder tap is installed correctly and will provide years of trouble-free service. Now, let's address some common misconceptions about transformer feeder taps. There are several common misconceptions about transformer feeder taps that can lead to improper installations and potentially unsafe conditions. One common misconception is that the feeder tap rules in 240.21 B3 always apply. As we discussed earlier, these rules only apply when the total length of the primary and secondary conductors is no greater than 25 feet. If the total length exceeds 25 feet, 210.20 must be used instead. Another common misconception is that the oct in the subpole only needs to protect the transformer. While it's important to protect the transformer from overcurrent, the oct also needs to protect the primary conductors. The oct should be sized to protect the conductor's ampacity, as determined by 210.20. A third common misconception is that voltage drop is not important for transformer feeder taps. Voltage drop is always important, especially when the tap conductors are long. Excessive voltage drop can lead to inefficient operation of equipment and potentially damage equipment. It's essential to consider voltage drop when sizing the tap conductors. A fourth common misconception is that grounding is not necessary for transformers. Grounding is essential for safety and helps to prevent electrical shock hazards. Transformers must be properly grounded according to the requirements of the NEC. A fifth common misconception is that any type of connector can be used for terminating tap conductors. Only approved connectors should be used for terminating tap conductors. The connectors must be properly sized and installed to ensure a secure and reliable connection. Avoiding these common misconceptions is crucial for ensuring the safe and reliable operation of transformer feeder taps. Always consult the NEC and other relevant standards and regulations when designing and installing electrical systems. If you are unsure about any aspect of the installation, consult with a qualified professional. Remember that electrical work can be dangerous, and it's always best to err on the side of caution. Now, let's consider some advanced topics related to transformer feeder taps. While the basic principles of transformer feeder taps are relatively straightforward, there are some advanced topics that are worth exploring. One advanced topic is the use of autotransformers. Autotransformers are a type of transformer that has only one winding, which is used for both the primary and secondary circuits. Autotransformers can be used to step up or step down voltage, but they do not provide electrical isolation between the primary and secondary circuits. Autotransformers are typically used in applications where electrical isolation is not required and where efficiency is a primary concern. Another advanced topic is the use of buck-boost transformers. Buck-boost transformers are small transformers that are used to slightly increase or decrease voltage. They are typically used to correct for voltage drops or to match the voltage requirements of specific equipment. Buck-boost transformers are often used in applications where the voltage supply is not stable or where the equipment is sensitive to voltage variations. A third advanced topic is the use of three-phase transformers. Three-phase transformers are used to transform three-phase power. They are typically used in industrial and commercial applications where large amounts of power are required. Three-phase transformers can be connected in various configurations such as Y-Y, Delta-Delta, and Y-Delta depending on the specific application requirements. A fourth advanced topic is the use of dry-type transformers. Dry-type transformers are transformers that do not use oil or other liquid coolants. They are typically used in indoor applications where there is a risk of fire or explosion. Dry-type transformers are more expensive than liquid-filled transformers, but they are safer and require less maintenance. A fifth advanced topic is the use of energy-efficient transformers. Energy-efficient transformers are designed to minimize energy losses and improve overall efficiency. They are typically used in applications where energy costs are a concern. Energy-efficient transformers can save significant amounts of energy over their lifespan, reducing operating costs and environmental impact. These advanced topics are just a few examples of the many complex issues that can arise when working with transformers. It's essential to have a thorough understanding of these topics to ensure that you are designing and installing electrical systems that are safe, reliable, and efficient. Remember to always consult the NEC and other relevant standards and regulations when working with transformers. If you are unsure about any aspect of the installation, consult with a qualified professional. Now, to recap the key points regarding transformer feeder taps and the application of 210.20, remember the following. Firstly, if the total length of the primary and secondary conductors exceeds 25 feet, 240.21. B3 does not apply, and 210.20 should be used for sizing both the primary conductor and the opt. Secondly, calculate the total load connected to the secondary side of the transformer to determine the minimum ampacity required for the primary conductor. Thirdly, voltage drop must be considered when sizing the conductors, as 210.20 accounts for the voltage drop over the length of the conductors. Fourthly, the opt must be sized to protect the primary conductors and should not exceed the conductor's ampacity. Fifthly, always consult the latest edition of the NEC and local amendments for specific requirements in your jurisdiction. By following these guidelines and understanding the principles behind them, you can ensure the safe and reliable operation of transformer feeder taps in electrical systems.